Okay, so we should be ready as well. So I will simply jump into it. This is the second part, and it's about implied volatility. And implied volatility is something we tend to back out from options. Option pricing is a huge area in and of itself. I'm a little bit less of an expert on option pricing than I arguably am on volatility modeling. That is said as a caveat. Also, what I will focus on in this lecture is option pricing as it is useful for me, the way I think of it, in terms of extracting volatility measures and forecasts. So it's a very particular slice of the option pricing literature that I will focus on, and it will kind of lay the foundation for the things that we will do this afternoon, and it should also be of interest, I hope, in and of itself. I am even worse than Tim in terms of providing references. There's so many references in option pricing that I basically just left them all out and only have specific references to equations and pictures from papers that I actually use in the presentation. So it's very much harder for people that I don't cite to get upset about that, I hope. So what is implied volatility and why do we worry about it? So I'm going to give a little introduction and then give an overview of what I will cover. Implied volatility is the volatility of the underlying returns that we extract, some measures we extract from volatility-sensitive asset prices. And it's typically associated with volatility measures we extract from option prices, but in principle, it could be from any other asset which is priced or is sensitive in terms of its pricing to an underlying volatility factor. The volatility that you imply are typically quoted as standard deviations per year, so they are annualized. That's one thing to keep in mind when almost all the numbers I'll show you are annualized volatilities. It also gets a little tricky when you say volatility and or variance. Volatility in the continuous time literature has a very specific meanings of being the sigma in the continuous time representation, and Tim and I have been using realized volatility usually for the variance, actually. So here in this context it gets somewhat important to distinguish the two, and I'll try to be a little bit more careful about what I call integrated variance and integrated volatility and things like that. So keep that in mind. It's the standard deviation and not its square. It's not the variance when we say implied volatility usually. We can imply volatility either through parametric models. We specify what the model should be and then back out what the implied volatility must be, or we can actually use non-parametric techniques. I will talk a little bit about both. Usually when you just say implied volatility from an option, you would think about the Black-Scholes implied options price, usually for an at-the-money option. But you could certainly also specify some other model, stochastic volatility model, that you think might fit the underlying asset a little bit better. And in that case, you could get an implied volatility from that model. And that has been done by a lot of authors that purport to provide a better fitting model. However, what will happen is that not everybody agrees that's the right model. So for standard purposes, people kind of refer back to the Black-Scholes. With that one caveat that in very recent years, this VIX measure, which is from the CBOE, or Chicago Board of Options Exchange, downtown from where I usually teach and work at Northwestern, they have this VIX measure, which actually is a model-free implied volatility measure. So that's been a bit of a breakthrough in this whole literature, and I think why both Tim and myself are quite excited about what you can do with this option implied, and in terms of comparison and contrasting with the realized volatility measures. But this is, I will talk much more about that, but that's a model-free implied volatility measure, and that is widely reported in the newspapers as a VIX, and you have the VDAX, is the equivalent here in Europe, I guess. And now you actually have to be careful when you say that the implied volatility of, I got some extra vocal power here, so there was something going on. So nowadays you actually have have to be a little careful as to whether you mean the Black-Scholes implied or the model-free implied. We'll discuss both concepts here. Why are we interested in these? As a basic motivation, they are based on observed market prices. You don't have to believe in a model, you can believe market prices. It clearly aggregates the view across many investors that have serious money at stake. It is not limited, as realized volatility or variance is, often to just looking at lag squared returns in terms of how it forecasts implicitly volatility. That is, if market participants expect an important policy announcement, a shift, a war, some other catastrophe, or good news, that could be incorporated in their forecast. It would be much harder to do using the realized variance of volatility framework. It implicitly embodies, hence, all available information. It's explicitly forward-looking, whereas realized volatility measures tend to kind of measure where we are now and then do some forecasting beyond that. These are explicitly forward-looking, and market efficiency would say, at a first order, these ought to be good forecasts. If they were terrible forecasts, people could make a lot of money speculating against them and prior trading. Okay, so that was the means of motivation. So what am I going to cover? I'm going to first kind of introduce you to the difference between the P and Q measures. Very fundamentally, what is the difference between the option prices implied measures and the ones that Tim talked about in the first lecture. Second, I will then move on to talk about how you actually construct these implied volatility surfaces. The surfaces means implied volatilities over time, so like a term structure of volatility, but also across strike prices, where you get smirks and smiles and things like that. So that whole surface is an input to anybody who does fancy derivatives pricing out in industry. They day by day extract these implied volatility surfaces. We need to do that as academics as well, to use them as good inputs to our forecast models. I will talk a little bit about what Black-Scholes does in terms of a volatility forecast, and then move on to these model-free variants that we have, and that includes the variance swaps. It turns out this pricing of variance swaps, which is a real thing that is traded out there in the markets, maps very nicely into the concept of what a model-free implied volatility or variance is. And I'll introduce this relatively new thing in academics, which are barrier and corridor implied volatilities, and use them both at the end of this lecture and a lot in what I do this afternoon, later on, next lecture. And finally, I will look at, since this is about volatility forecasting, I will try to evaluate, at least this, first cut, how various different implied volatility measures from options, of which there are many, which ones are actually better at forecasting the actual realized volatility and how you would go about doing that. So that's the overview. I will try to keep you abreast of where I am in these 5 points as we move along. So first, a short introduction to what many of you already, I'm sure, know. That is the difference between P and Q measures. So Tim's discussion this morning was exclusively about the actual stock price or exchange rate or whatever the underlying asset was. We call that the physical or actual or objective probability measure, P, traditionally in the literature. And if we have a price evolution of some speculative asset, I'm not going to use the log price as Tim typically did. I'm going to use the spot price, here S. If you assume no dividends, and in the Black-Scholes model, we will typically have that these mean and volatility coefficients either be constant or at least deterministic. You can generalize the theory to allow for deterministic path of these. Then we would have the standard setting. You could add jumps here and everything would go through with some approximations, so let me not bother you with that generalization. But so the basic framework we're going to think about is continuous time asset pricing, where we have a drift and a volatility coefficient. If you divide ST over here, you'll see this is a percentage increase basically, is mu TDT, and sigma, this is our stochastic volatility in general. On the Black-Scholes, that would be deterministic or constant. And what is important is basically just the average of that over the horizon we're looking at. So I can define mu, the mean return from T to cap T, as just this average strength of that volatility coefficient. If it's deterministic, it's almost like treating it constant at that rate. And then what we do in asset pricing, and this is obviously almost by definition true, if we look at the expected value of our asset cap T periods forward, a month forward, let's say, at time T, we take the expectation under the P measure, and that is the expected price. This is just a definition. This is my information set. So if that is the expected return, this just holds by definition. You get the ST, where we are now, times the cumulative returns that are expected to arise. That means we get the current price by discounting the expected future value of this asset. This is, again, just true by definition, but notice here we discount with the risky expected return in the general setting. Now that's just by definition, but it points to what asset pricing actually has to do under the P measure. We have to kind of, this holds more generally. If you wanted to look at a payoff structure that had some payoff at time cap T, T plus cap T, you just evaluate the expected return of that or expected payoff, and you have to discount it back. But unfortunately, you have to discount it back at this mu, which has to reflect the systematic risk of that asset, and people disagree about that, and it's kind of hard to come up with the exact right mu. So in general, this is a hard exercise to do. It almost just defines the mu here, but in reality, this is hard to use in derivatives pricing. So under the P measure, you could do this, but you need to know exactly how to price the expected return on this asset and create this expectation here. If we go to the Q measure, which is where the option pricing lives, we can do a little bit of change of measure, and that's what people traditionally do. We think of this as the risk neutral or pricing or martingale probability measure Q. So we have exactly the same structure, a diffusion like this. Under no arbitrage, this tends for many assets to be larger than the risk-free rate. So you get a higher return than the risk-free rate. You could also get a smaller depending on the riskiness of the asset, systematic risk. But under no arbitrage conditions, it's not always. There's some states of nature where you get less than the risk-free rate, some states of nature where you get more. Now, what the fundamental theorem says is that you can reallocate probabilities a little bit, so the pieces that have higher expected returns than the risk-free rate, you put less probability mass on, and the ones that have less than the risk-free rate, you put more probability mass on, and you get an alternative representation where the asset earns exactly the risk-free rate, and this dW, it becomes dW star. This accounts for the change of measure. Okay, once you do that, all risky assets that's priced this way can actually be thought of as earning the risk-free rate. So when you look at a general payoff, in this case just the asset's value at time t plus cap t, under the Q measure, Tim called it a star, so I just wanted to indicate this is the same as his star he had when he priced options. It's actually now accumulating expected returns at the risk-free rate, which means you get the current price under more generally a general payoff as the expected value of that payoff under the Q measure discounted back at the risk-free rate. That has simplified our problems greatly because, one, the risk-free rate is known to a very, very good approximation, at least by just looking at the LIBOR curve or the treasury bill curve or whatever you want to think of as the appropriate risk-free rate for your asset. And then here we need to find the probability measure, this expectation under the Q measure. That seems daunting at first, but the fact is that lots of derivatives are traded that are a function of this, and we can actually learn a lot about this expectation from seeing right there the prices of options that are traded. So this simplifies matters greatly given the fact that we have liquid market prices. It tells us a lot about that guy, and this guy is easy, so suddenly derivatives pricing becomes much easier. And that's the general kind of setting that we're in. Let me also then define formally what the Black-Scholes implied volatility is. Tim gave you already this formula. Under the Q measure, we're just looking at this payoff. On here, a call option, here, a put option. And you all know the formulas. You take the expectation of that payoff under the Q measure and discount it back at the risk-free rate appropriately, and then you get the value of the call option and the put option. Now, what I was saying before about learning a lot about the expectations under the Q measure, imagine I will kind of talk about things I'm going to address later on, but imagine you had a lot of different strike prices at that maturity t plus cap t, and you change k a little bit and you can see how the option price changes. All that changes here is, this is the same discount factor, all that changes here, if you change k a little bit, you move k up a little bit, is okay, and now the difference between the two option prices must reflect the expectation that st plus cap t is between the previous little k and the new k. So if I move that k a little bit, I get a lot of information about the expectation that the price will be in that little range. And if I have a whole cross-section of those strike prices, I clearly can map out the probabilities of being in different parts of that domain very straightforwardly. And that's really why option prices are so informative. So notice I made little changes in k to get probabilities. If I take double derivatives, I might get densities, and that's actually what I will get formally later on. Okay, so Black-Scholes formula makes some simplifying assumptions. As I mentioned before, the mean and the variance are deterministic. You can think of them as constant. And that implies that the underlying stock price or asset price would be log normal and mean and variance that are functions of the risk-free rate. More generally, if you allow for dividends, this is a dividend payout ratio that you don't get if you have to wait to buy the underlying later on. So that becomes a discount in the stock and the option price from the, but that's fine. We can account for that pretty straightforwardly. And then the variance here will be, as Tim explained, basically captured with what I call the quadratic variation, but it could also be the integrated variance or integrated volatility that Tim was talking about over this horizon. Okay, so what the Black-Scholes implied volatility measure, of course, does is sigma Black-Scholes implied variance solves is for a given set of inputs. Strike price is being very important, and but the risk-free rate and maturity and stuff like that. You have an option, closed form option pricing formula for that, because I assumed a distribution, so I could evaluate this thing directly, assuming my closed form solution and distribution of ST in the future. So I can set that equal to an absurd market option price. I just need one option price. I put it here, and then I put over here what the Black-Scholes formula says it should be, except for the sigma, and then I find the sigma that solves this equation. Okay? Why can I always do that? Because the Black-Scholes option price is monotonic and increasing in the volatility. The more volatility, the more valuable is this European option price. So it's a straightforward exercise. In other words, the Black-Scholes option price is monotonic and increasing sigma, so there's a one-to-one mapping between an option price and an implied Black-Scholes volatility. In fact, so much that option traders tend to quote not the option price on a given option, but the Black-Scholes implied volatility they use that corresponds to that price. Okay? So what I'm saying is it's completely equivalent to quote options in the price of the option or in the implied Black-Scholes volatility. There's a unique mapping between the two, and then the option trader in the old days would have a little calculator that mapped between the two very quickly. Why has that become so popular? Actually, it's a more natural metric to tell you what the implied volatility is than it is to tell you the actual price in dollars. Now imagine that you were looking, I gave you two option prices, the option price on a 2-month in the money put option, it could be 5% in the money, and another one that was 1 year out and was at the money call option. And now you are asked to evaluate which one is priced dearly or highly, which one is expensive, which one is not. Well, it's very hard to very quickly account for the put, how far it's out of the money, what the strike price is. It's much easier to compare the two if I tell you what the implied volatility is on one versus the other. The one with a higher implied volatility in some sense is priced more expensively. Now, that's exactly the same type of thing that people do with coupon bonds of 2 years versus 10 years maturity, and they tell you the yield to maturity as a simple way of communicating the $850 price on one versus $565 price of the other, which is very hard to assess in terms of relative priciness. But the yield to maturity is easy to understand on coupon bonds with different coupons. The same thing for these option prices. So it's become customary to price options just in the Black-Scholes implied volatilities, exactly as it is to say yield to maturity for bonds. Okay, just a little bit about Black-Scholes implied volatilities. If you think of them just as price devices, there's nothing inherently incoherent about those. Even if the Black-Scholes model doesn't work, it's just a different way of pricing options, and that's absolutely fine. And so you can actually convey the pricing of options more succinctly in the implied volatility surface from the Black-Scholes model, and here's an example of that. This is for the FTSE, the British stock index, and you have maturities out here and you have strikes this way. So you see at the very short maturity you have a very steep smirk. When you get to out of the money put options, volatilities get high. That means option prices out there are relatively expensive, at least viewed from the Black-Scholes benchmark. The skewness declines as you move out. You get a flatter structure, and also seems to here that the volatilities are decreasing a little bit in this dimension. But these are the type of surface that people back out every day. This surface tells you a lot about how the market is pricing anything that's a function of the stock price, the stock index at that maturity. At these different maturities going forward, and that's what's input to all these derivatives pricings. That's also going to be the input to our implied volatility measures. Okay, so here another example of different skews you can get. I took this from Liu and Wu's lecture notes, but you can find examples of this all over the place. This is for a single stock AMD in the US. Here in the short term you have what looks pretty much like a smile, and the longer maturities you get a smirk. So this is for one maturity, it's like a cross-section of that whole surface for one maturity. If you look at an index, you typically get skews all over the place at the different maturities, so you have different slices here. And finally, if you do this for currency options, you get more smiles and smirks. They are much more symmetric. This is for the yen and the British pound versus the US dollar. Okay, so that's kind of the patterns you see. Now, it obviously immediately says Black-Scholes, would think of, at least if you assume volatility to be constant, should be a completely flat surface, and that's not what we have. At this point, it's not a huge problem. It's just a matter of explaining to us how the options are priced, which ones are expensive versus others in some sense. Now, let me talk a little bit about how I think about constructing this whole IV surface. That's actually an important input to anything you do, and it's quite important in some context. How do you get this implied volatility surface, or how do you get to extract pricing information out of the options that you see more generally? Okay, so I'm doing that before we get to these other things. So this is again kind of an input to the process that I think is worth thinking about. Now, so constructing these surfaces, price surfaces, we want in some sense some smooth implied variance of volatilities or smooth option pricing surfaces. We think there might be arbitrage if they have a lot of jiggered surfaces. Basically, you can show that we would expect them to be smooth under very standard assumptions. So because they're bid-ask spreads on actually traded options and short-lived ones have irregularities and other things, you don't get it necessarily to be very smooth. So in some sense, you want to find a procedure where you can bag out the implied volatilities at different strikes and different maturities, and then we need a procedure to connect the dots that kind of makes it smooth in some sensible way. And there's various ways of going at it, and it's been proposed by different people to go all different ways. You can either you just basically have a surface of option prices, and you want to kind of fit the surface through the option prices. That becomes, some of the prices are really low, and some of the prices are really high, so you get a lot of variation in the surface, and it arguably is a very hard task to do it that way. More popular is to go directly to the option implied variance of volatility surface. Basically, you have the implied volatilities I showed you, and I showed you just the dots connected by lines, and that's kind of what I did. I connected the dots. Now, more fancifully, you can actually extract the whole risk-neutral density directly, which is what I would actually prefer, and I'll talk about that. So these two methods are probably the ones that I use the most. You could do it directly with a specific model. You can impose a model and then extract what all these prices ought to be. You calibrate the parameters to fit the best, and then you say whatever deviation there is from the observed prices to my model price are just measurement error. And then you just draw the lines, right? Or you can, so you can do that with any model, Black-Scholes, Merton model, but you can also add all kinds of twists and whistles that would give you the skews and some term structure volatility. But it would be model dependent, and not everybody would necessarily agree with your model. So clearly what industry, and what I prefer as well, is to try and say, impose as few assumptions as possible, let the data talk, and get some model-free measure, which is very appealing. We have model-free realized variance of volatility. Why not try and get model-free implied volatilities as well? But what is better and more accurate and robust? It's a huge literature. I'm not going to give you the answer necessarily, but I'm going to give you what I think are a very sensible way to go, and that's everything else I does later that builds on my own work would refer to that particular method. Okay, so if you use a parametric model, and I'm going to be very brief on that because that's really not what I'm going to do, but you could, then you could let the model on the Q measure have n parameters, so you parameterize that risk-neutral density or risk-neutral data generating process by n parameters. It could be a Gauge model, stochastic volatility model. Call that parameter vector theta, okay? And then you could look at the option prices, a whole vector of option prices. There could be hundreds of these. And now they have to have a certain particular price depending on the values of those parameters, okay? If you assume they are observed without error, you can use n option prices and back out exactly n parameters. So Black-Scholes uses one parameter and one option price. You'll go from price to sigma, and that's it. Now, generally, you can introduce n parameters and n option prices, and you can back out exactly. If you know the affine term structure models or affine option pricing models, that's effectively one of the ways that people did in the early literature is they chose n bonds, and then they exactly extracted the n parameters of the affine model. That's also done in option prices sometimes. Okay, so you fit these prices perfectly by doing this match. Well, there are more options out there, so you can look at the pricing errors on the other options that you didn't fit to and see if they look IID distributed around some extracted model price. So people do that a lot in the bond pricing literature and a bit in the option pricing literature. More sensibly, I think, is to try and use the information in all the option prices. What do you then do? You then acknowledge that the option prices are observed with error, and then you use all reliable option prices. That is in itself a task. Which option prices should you throw away? The ones that violate some arbitrage conditions. Maybe if the bid-ask spread is too big, if the volume is too low. There's all kinds of different ways of figuring out which option prices should you take seriously and which not. Should you weigh them depending on how important they are? I don't know the answer to all of that. But you can have many option prices, and then you try to minimize the distance between the model implied and the ones you observe in some sense. And that minimizer gives you the parameters, and that defines what the option prices should be for all strikes and times to maturity. And the problem with doing that is it's often when you're looking at the option pricing space, it becomes a very highly nonlinear function of the option prices. It becomes very sensitive to pricing error and the particular metric you use here to evaluate these things, and there are papers about that. And there are certainly sensible things to do, but there's a lot of heterogeneity in price across strikes and times to maturity. And depending on the economic objective, do you want to hedge, do you want to price derivatives on these plain vanilla stuff or more advanced derivatives? People find that it matters a lot for what might be the better procedure to apply. So there's a lot of interesting research questions when you impose a model and try to extract that. People can also become more parametric, non-parametric, and I'll get to that shortly. But why couldn't you just go and use the Black-Scholes implied volatilities themselves? I gave you some nice pictures already, right? Why not just draw some smooth lines? So this is kind of going non-parametric in some sense, because option prices are the same as implied volatilities. So before I did it directly in the option prices, let's instead do it in the implied volatilities. There things look a little bit more regular and sensible, right? So why can't we just draw lines through the Black-Scholes implied volatilities and use that surface somehow? Well, you can do that with all kinds of non-parametric curve fitting techniques and flexible local non-parametric techniques of all kinds. People here in Berlin are very good at this stuff, and they could give you some procedures that work well. So one of the problems I've found with this is it's almost too flexible. It is sensitive to pricing errors. You need some way of disciplining this. And it turns out for some derivatives written on that are a little more complicated, small deviations, small errors in this Black-Scholes implied variance of volatility gives you really big pricing errors because the risk neutral density is off in one corner, and this derivative tends to be sensitive on that tail or something like that. When you do this, it's very hard to impose the right shape restrictions. By that I mean it actually turns out generally characterizing what the risk absence of arbitrage means for this surface is non-trivial. When you do these curves, you should really obey that, because otherwise you find that you think you can do some arbitrage when you look at the risk neutral density that follows from these. Okay, so it's hard to guarantee this arbitrage-free shape because implied volatility is not given that it comes from the non-true model. It's hard to take that shape and think about arbitrage from a more general model. So it's very hard to actually, and when you have bid-ask spreads that are non-negligible for some of these options, it becomes hard to actually do this really well. And so the implication of all of this is sometimes you get a risk neutral density that's not very smooth out of this. And the risk neutral density is actually what you use to price everything. And I'll get to that shortly. So, in fact, right away. Okay, so you could go in this implied volatility surfaces, but it's not, it doesn't solve all the problems. Instead, we tend to, in the modern literature, look directly at the risk neutral density. And so we already seen that a put and a call option is priced just by this expected value, expected payoff, discounted back at the risk-free rate. Well, writing that out a little bit means we take the payoff against a density. We evaluate that the density that characterizes the probability distribution of that terminal value at the maturity of the asset in question. So we just need to evaluate, we need to find this guy, right? And then I can easily price the option. So anything that can give me this risk neutral density will allow me to price anything, and I can infer everything else. So it is a method in which I can extract this risk neutral density directly. And indeed there should be. In fact, if you take this double derivative with respect to the strike price of either the puts or the calls, as I kind of intuitively argued before, you would actually get the risk neutral density exactly at that point. So point by point, as you vary k and you do this integration, you should get this risk neutral density. Well, that doesn't quite answer it because we're trying to figure out how to price these. So if I know how to price them, I know that one, and vice versa. But it's still a useful insight because we can then start thinking about more generally how to take all these option prices and in one step infer that risk neutral density. And that risk neutral density is nice because we can easily impose shapes on that makes it arbitrage free. Okay? So to repeat myself a little bit, any future payoff G that's a function of the terminal value at that maturity date of the underlying asset will be just the discounted value at the risk-free rate of that expected value. So we need this guy. Okay. Now there are different ways you can get at this. You could use the Black-Scholes implied volatility, and if you did that, what you would do, and this is actually why it gets tricky to use Black-Scholes implied volatility, you could fit smoothly the Black-Scholes implied volatilities, but then if you wanted to get the risk-neutral density, you would have to infer that back to the actual option prices and then take a double derivative of that. So you have some smooth surface in some way, flexibly estimated. Now you have to infer what is the corresponding prices everywhere and then take double derivatives. When you take double derivatives, you create jags. It's a distorting function. So things that are relatively smooth can start having kinks and other things in it. Okay, it's not a smoothing operation, but the opposite when you differentiate. So what we want to do instead is we actually want to try and avoid that and get to where we integrate instead, which is smoothing functions. So what do? Well, write the risk-neutral density as a flexible, smooth family of densities. Okay? So now just take, and this you can do semi-non-parametrically. You can take some densities that are well-behaved, and then you can mix them. You can take a little bit of weight on one, and third, second, third, fourth, and fifth. If you don't pre-specify how many there are, you get a semi-non-parametric in the sense you can do an expansion in the number of terms there are. And then what you want to do is you want to fit the option prices by minimizing the distance between model option prices and the observed market prices. How do you do that? Well, go back and you see you do this integration. So I come up with a proposal density, then I figure out what are the prices, and I see how well I can match the prices that I have with that density to the observed market prices. And I then optimize by changing these risk-neutral densities a little bit by changing the parameters and the number of densities that are underlying that. Okay, so that's what's happening here. This integration produces smooth outcomes, and instead of doing double differentiation that amplifies noise and irregularity, you get smooth surfaces. And that means the risk-neutral density implied option prices can then be used if you actually want to display the implied Black-Scholes implied volatility surface. It's very easy. Once you have the risk-neutral density, right, that I can fit to fit the option price as best possible, I can then very easily just look at what is the at-the-money implied volatility at a given maturity that's implied by that. So I can very easily go back and portray the whole surface this way if I want. But more fundamentally, I actually have this one directly. And you can estimate that day by day, this volatility surface, or this risk-neutral density implied by it, day by day. There's a huge literature on this. I just already kind of verbally talked about one way to do this. Parametric densities you can specify underlying this that you integrate up to see if you can get the option price, or semi-non-parametric ones and use, I could give a ton of references to all these methods. The one that I like was developed by a co-author that I worked with lately called Oleg Bondarenko from the University of Illinois, Chicago. We use in our joint work positive convolution approximation, which is a semi-non-parametric procedure. It kind of avoids overfitting. There's only a few densities that we mix log normal densities. We can actually allow for relatively small sample and still get sensible results. We always get an arbitrage-free density out, and it's computationally quite simple. And you can do this day by day, and you get very robust results. But I'm not saying it's necessarily the best. There are certainly other techniques out there. As an illustration from all these bigger principles about how to extract information out of option prices, here is just for one day. This is from the S&P 500 options data on, I guess it's April 19th, 2000, and there were 21 trading days to maturity, which is basically 1 month. So what we had here is this happens to be a very liquid option markets on these S&P 500 futures. So here's the implied volatility from the Black-Scholes. You can see there's tons of observations here. This is moneyness. So here the out of the money for the put options, here the out of the money for the call options. Here is the option prices that were observed. Again, carefully we take midpoint of bid and ask and various sorting procedures, but it's not too hard given the liquidity of this market. And what this is the option prices divided by the price of the underlying. So you were paying premium and the max at the money about 3% of the underlying for this option out 1 month. At the money, this is out of the money put options, these are out of the money call options as percentage of the underlying. Of course, as you go out of the money, option prices drop, and so that's what you're seeing here, the decay. If you imply what the risk neutral density is from this distribution, or this observations here, our method gives us this smooth risk neutral density. You can see the slope to the left, which is basically saying tail events to the left. Market expects, if you thought this was true expectations, market expects there must be a much bigger chance of big movements to the downside than the upside on the S&P 500. That's partially the pricing of the options rather than the truth. And you can of course also get the cumulative density function out of that. So here that is. Okay, but this is our risk neutral density on this day. Now we have some 2,000 days. So you do this every day at the end of the day at the official settlement prices of the options. You can get every single day a measure of this risk neutral density going forward 1 month, but you could also do it 3 months or 6 months, depending on where you have liquid options. Now there's a little bit of you have to interpolate between if there's only 3-week options and 6-week options, you have to kind of interpolate to get that 1 month. But otherwise, this is a very robust procedure, and that doesn't introduce many mistakes anyway. Okay. So we can do this, and there's a big literature on it. I gave you a little bit of my methodology as to what I think is the useful way to go, and some of the caveats. But it's a huge field in and of itself, and lots of research is ongoing. And every investment bank you'll go to and has a derivatives desk would have some guys doing some of this, for sure. Okay, now let me talk a little bit about Black-Scholes implied volatilities as a forecast of volatility going forward, its advantages and disadvantages in particular. And then, of course, we're going to have to move to these model-free ones, which is really the truly exciting and innovative concept that's arisen in the last few years. And then finally, I have this examination of predictability. So, what people do with Black-Scholes is that they say, okay, it's actually a fairly robust measure if you go at the money. So go back around before 2000, 2002 or something like that. People were saying the at the money Black-Scholes implied volatility is a pretty good measure in the sense it's robust. If you want to look at how it behaves with volatility, you find that the implied volatility back out from the Black-Scholes option pricing formula is completely linear in the actual underlying volatility. So if I let volatility move this direction, at the money you get this blue line. If you're a little bit out of the money and in the money, you can get nonlinearities, which actually explains why people were more comfortable using at the money. You got more liquid options trading there, but you also had this linearity in the option price. So if you somehow got a slightly off, you can kind of interpolate between the bid volatility and the ask volatility, or you could look at different options with slightly different volatilities, and you feel comfortable just linearly interpolating given this. If they both have measurement errors that are linear in volatility, you can kind of interpolate and get a better and reasonable estimate. So people felt that was a nice property. And the same thing holds in terms of maturity, time to maturity, which is here. It's almost linear, but you get some bad nonlinearities if you get too close. The maturity is too short or something like that. But by and large, this is a fairly robust technology. Here's what the Black-Scholes implied volatilities would look like if we plot them out. This is something that we extracted ourselves. So this is Andersen, Bondarenko, I guess, Black-Scholes implied volatilities. And using this estimated risk neutral density, figuring out what this option price should cost at the 1 month maturity at the money, and then get the associated Black-Scholes implied volatility. You see here in 2008, we'll be able to update it here. We get this huge spike, which goes up almost to 80%, but not above. And you have the usual tech bubble stuff here, and the Asian crisis here, Russian crisis, I should say, here, and the LTCM. And otherwise, this is what Tim called a low volatility period here, and you kind of see that evident. There's a huge, it might not look that dramatic, but this goes from like 10% up to 80, and even 10 to 40 is pretty dramatic. So there is a lot of variation in volatility. If you're looking at variances, you square these, and the differences become huge, obviously. I should say this corresponds very much, doing this corresponds very much to the measure that the CBOE used to have on the implied volatility, which is called the old VIX nowadays. VXO is the symbol, not VIX anymore. However, the old VIX, which they are still updating, you'll still find it on the web page, the Chicago Board Options Exchange, uses the S&P 100 as the underlying asset, and they have some American features as well. So it's not identical to this, but it's going to look very similar. Okay, so that's the old-fashioned method. So,
Do you allow a question in between? Is it allowed?
Do we, Nicholas?
Afterwards.
No, is the answer. Okay, so obviously Black-Scholes is not perfect, right? So it's inherently contradictory because we assume volatility is constant or deterministic. It clearly is very stochastic and it varies over time, and log returns are not normally distributed, which I'm assuming. Tim said they might be log normally mixtured, which is very different than just assuming they are log normally distributed. So this just doesn't work. So it's model dependent. It's not interpretable as the expected volatility if the Black-Scholes model is invalid, at least in an academic sense. We don't really know what it is we're doing. We think intuitively it makes sense, but it's not directly interpretable as expected volatility. It's not associated with any pure volatility contract. You can't write a contract on this and think of this as the price of that or something like that. It turns out this model-free new VIX concept exactly has that feature. So there's lots of reasons why people went away from this. And in recent years, when volatility contracts started to be traded in over the counter in New York and other places around the world, it happened not to build on the Black-Scholes implied volatility, but this model-free implied volatility. So there's the financial sector itself for telling us there are better concepts out there. And those are directly interpretable expected volatility. So I'm now moving from these Black-Scholes measures to these new measures that people have adopted, people trade on, and is the basis for the CBOS volatility index, the VIX. And basis for our lots of academic studies about the contrast between the P and the Q measure volatilities, basically volatility risk premiums that we're going to discuss in the next lecture, lecture 3. So I'm moving here to part number 4. What we covered already was a little bit of introduction between the P and Q. Everything here is on the Q. Black-Scholes prices can be interpreted as basically another way, or implied volatility is just another way of quoting prices. We thought about how to construct this surface and extract risk neutral densities, and kind of looked at Black-Scholes as being one forecast. Let me say already that I didn't waste my time by showing you those Black-Scholes forecasts, because it turns out the Black-Scholes implied volatility forecast, if you think of it as forecast of the volatility of the underlying asset, turns out to be quite good and arguably actually better than these model-free ones. And we'll talk a little bit about why that happens in this lecture and much more in the next lecture. So Black-Scholes implied volatilities are not terrible if you want to think of them as actual volatility forecasts, in spite of their limitations. Okay, but let's get to this model-free, and this is where I get a little more technical, and well, I was technical before in terms of the implied variance surface, but I kind of jumped past all the difficulties. Here I will talk a little bit about the principles that underlie this, because it is kind of important, and it's simple in some ways, but I'm not going to go into depth. It's not a real attempt to so that you can understand all details. But I think intuitively you'll grasp a little bit about what pieces you have to put together to understand where this model-free implied volatility comes from, and then generalizations that I'm going to use hinge on that. So it is important for me. So here, as I said, I'm not going to call it IV, as Tim did. It's now implied variance, which is important because volatilities and variances are different in this context of option pricing. The volatilities are basically the square roots of these guys. So I have to be explicit in my notation. I'll try to be just writing IVA when there's a variance that's involved. So this is the integrated variance that Tim has talked about. We approximate it by the cumulative sum of, here my delta is 1 over n, so n is the number of times we observe it over the period we are measuring the volatility. We also call that the realized variance or realized volatility observed at the n is the observation frequency over that interval. Now that's an ex post measure, and it's under the P measure, as Tim explained, right? So we have the data, and then we look at what was volatility in the last month or the last day. We're looking back, we have the data. Now that can be useful for forecasting, but in and of itself, it's an ex post measure of what the volatility actually was, hence the realized notation. Now, if you want to think about variance forecast or the variance going forward, we actually need to create the expectation of that measure at time 0. Now we're looking forward, and we're trying to forecast what is this measure, what is this guy or this guy going to be over the next month. Well, we can do that by just putting expectations on and doing it prior to the period. So we want to evaluate data under the P measure, and this is what a volatility forecast would look like if you believe in realized volatility and you were in the world that Tim was in. Now, what we are going to do now is we're going to go to the model-free implied variance that comes out of options. We're going to be valuing exactly the same, taking the expectation of exactly the same quantity, this integrated variance, but under the Q measure instead of the P measure. And so we're going to get the expected value under the Q measure of the integrated variance. Again, this is an ex-ante measure, and that's what options always do. Options reflect, they are market prices of something that's resolved in the future. So it's a forward-looking expectation. And I'm going to explain why this comes out. As you know, I've not explained where this equation comes from, why model free. But that's what you ideally would want to get out of options. It's an evaluation of this quadratic variation or realized variance over the next month. And the best you can do with options is on the Q measure, because that's how we price things in this derivatives world, how we can back out information from options. So just to reconfirm, this model-free implied variance will be approximately the same as under the Q measure, estimating or forecasting what the realized variance will be, estimated as best we can at this sampling frequency n, right? So that's the same approximation as we're doing up here. This is not exact, but if we have a nice high frequency data, we're going to get a pretty good coherence here. Okay, so the model-free implied variance we would like to get is the expected return variation under the Q measure. Okay, so P versus Q, it's important. Now, it turns out that industries figured out something based on papers that have been appearing in the 1990s, but really kind of coalesced by 2000, 2001, I guess. There's a contract called the variance swap, and it turns out the price of this variance swap is exactly what I introduced on the previous page, this model-free implied variance. So that's intriguing, very intriguing. You're literally writing contracts and pricing the realized volatilities that I've been working on for so many years directly in the financial markets. It's beautiful. So I was very excited when I saw this. This is not my theory. This is adapted from the literature. There'll be a couple of references later. So what is a variance swap? If you're the long party, if you buy a variance swap from one of these investment banks in New York that's willing to write it to you, what do? Well, it's actually a futures contract. Swap is kind of a misnomer. It's called a swap, but it's a futures contract. So in a futures contract, you sign something today, then you get something against the payment, fixed payment in the future. That's what a futures contract is. You buy something at F, and it turns out to have a different value. Okay? So it's very close to a forward. I'm going to think it almost equivalent to a forward contract. So what is the payment at time t? So actually you should think of this as a forward contract, not a futures. Okay, what is the payment at the maturity? Well, what you're going to get is, and they have a way of defining the realized variance between now and then. They actually use the daily squared returns, but if they could, they would like to use more frequently observed. So in principle, any measure, good measure, realized volatility, if you take, that's what you're going to get. You're going to get the realized volatility at the end here. Okay, so if you see these cumulative squared returns from now till the end of the month being this, that's what you get. What do you pay for that? Well, according to theory, we just have to take this and evaluate an expectation, and that will be the fair price of that. So again, here comes the beauty of derivatives pricing. Since we don't have to discount because we only pay out there's no discounting on the risk-free rate even, we are just looking at, this is a payoff. They promise to give you something that's very close to the integrated variance, namely the realized variance over that period. How do you price it? You just take the expectation of that under the Q measure and you're done. This is what the investment banks would do, except they jag up the price a little bit to give you, to make some money on it. But the theoretically fair price would be this one. And if there's a lot of market participants in the market, they would drive the price pretty close to this. Okay? So you get the expected value of the integrated variance as the price of these variance swaps. So that's kind of nifty. The variance contract payoff is literally the cumulative variance over the future horizon. The expected profit you make on this. So if you bought one of those, how much money do you expect to get? Well, the simple answer would be zero because if you're pricing it at that price. But that's not true because realized variance is on the underlying. That occurs under the P measure. This is literally squared returns that happen and not under the Q measure. So what you're going to get is, when you're looking forward, you're going to get the expected value of this guy. And what you pay for it is the expected value on the Q measure. So the variance risk premium, the expected profit you get from buying this variance swap, is exactly going to be the difference between the realized variance under the P measure and under the Q measure. How the financial markets price them and how they expect it to be realized on the underlying itself. Okay? So you can stare at that a little bit and say, gee, that's kind of interesting. I could create some time series and look at what is the expected, what is realized variance, what do I on average earn on those, and then I can look at what do I on average pay on those. And if I had a lot of variance swaps, I could kind of look at how they were priced. Variance swaps are very hard, however, to get good data on. So we're going to go back to the options exchange and find a different way of coming up with this measure. And that's what I'm going to spend a few technical details on. But in principle, you could just look at those prices and compare it to this guy. I'm going to tell you how to get this guy shortly. Now, you can also think about this to the extent this is directly tradable using a portfolio of options or directly on variance swaps. You can actually define artificially a return on this. What would the return be? It would be what you get divided by what you pay, right? So with forward contracts, it's a little difficult. You don't put out any money. There's just this exchange at the end. But one way you think about the return would be what you receive over what you paid, minus 1. So you get this positive or negative return on this variance swap. And this afternoon, we're going to spend a lot of time looking at the sign of this thing. It turns out to be negative, okay, typically, and sometimes pretty big negative number. But we'll get to that later. Now, before I get into the details, I can plot the option extracted model-free implied volatility, okay? And here it is over the same period, all the way up to the end of 2008. Now we go over 80%. So the model-free implied, the VIX in other words, is above 80% where the Black-Scholes wasn't, if you remember. And if I have to draw the Black-Scholes and the model-free next to each other, you can see that the red, which is the model-free, is almost always above, basically it's always above the Black-Scholes in the S&P 500 for the US equity market. So there's something happens when I go from Black-Scholes to model-free that moves up the estimate, that inflates the estimate upward. Okay? So that's interesting in and of itself, but you can see these are very high values, as if the market prices options quite highly. Okay, more about that. Let me talk about, okay, very good. Let me then move to the details, a little bit more, so follow me along for 10 minutes of a little more technical details. I want to extract the model-free implied volatility for futures options because I do not see these variance swaps trading very much. It's very difficult to find good observations. They are mostly on individual options. If I want to do this market-wide, I need to go and find more liquid prices that are traded reliably every day at a very fine graduation in strikes. And one such place is the S&P 500 futures contracts traded not at the Chicago Board of Options Exchange, but the Chicago Mercantile Exchange, CME Group these days, because they merged with the CBOT, Chicago Board of Options Trade. So it's now the world's largest. They also bought NYMEX actually, so it's now the world's largest futures and options exchange. So they have a very liquid market on S&P 500 futures contracts and options on those. And we can use those very nicely in this context, and they are very gracious with their data. You can actually buy these data from them. So imagine that you have a futures contract that expires at some point cap T. Now you can write options on those as long as your maturity date on the options is before the expiration of the futures contracts, obviously. There has to be a futures price when the option expires. And so that's what we're doing here. We write options on that point. So my cap T corresponds to the same notation that I had for the maturity of the options before. They're just written on futures contracts that expire later on. So now you can forget about that complication. Just think of the futures as the underlying. The volatility of the futures is going to be the same as the volatility of the S&P 500 itself. Okay, at least in theory. So now we have this usual pricing information, except pricing formulas, except now the futures contract appears instead of the spot index for the S&P 500. Now that's kind of nice because the S&P 500 has a lot of issues about not all the 500 stocks being traded exactly at the same time. The futures prices aggregates this very nicely, so they are more reliable, up-to-date information anyway. So there's an advantage going to the futures market. It's very easy for people to hedge and do other things as well. So here we go. How would you then come up with a model-free implied variance measure? And it has two pieces to it. assume you have a payoff function, G. It could be any asset, and later on we are of course going to make it a specific asset, but if you have any function or payoff as a function of what the futures price is at a given point in the future, and it's a smooth function, so it has two derivatives, finite second derivative. So it's a smooth function. Then it can be proven, Kahn-Medan gives a formal proof, that you can have payoff spanning, okay? So imagine you can have strike prices, there's an infinite number of strike prices at a given maturity. In reality, they are a little bit apart, so there's some discreteness. You have to do a little bit of interpolation. But as these approximations go in economics and finance, this is actually a very good one at the right maturities. So you have a very finely meshed set of strikes across. Okay, now option price payoffs are either of that form or that form, depending on whether you have a put option or a call option. So you have a huge number of these hockey sticks smoothly distributed across the strikes or the domain of the futures price. You will not be too surprised to realize that a smooth function of the futures price can then be written as an infinite average sum of those prices of payoffs of puts and calls. Why is that? Well, you know you have spectral representation theorems that says any smooth function can be written as an infinite linear combination of cosines and sine functions. It's essentially the same type of theorem. It's spectral representation. It just says that any function, smooth function, can be seen as a weighted average of all these different puts and call payoffs. Okay, so you've got to buy that. It's called payoff spanning, and it's actually Steve Ross had a very early paper that said option trading helps increase efficiency because that spans the space in this particular way. Once you can trade options, you can trade on pieces of the risk neutral distribution, and you get a nice type of spanning. So it was called options and efficiency, basically, saying that you get more complete markets as you introduce more and more options in this particular sense. So it's very related to this idea. Formally, we're going to use the representation that's given in Kahn-Medan because it's very pretty. So look at this. You have the payoff. This is the payoff we're interested in. You can pick any point x, positive x, and then you take a first order approximation around that, and then you get this average of the payoffs of here the put option and the call option. And I'm going to take x equal to f0. That means we are looking at all out of the money put options here and all out of the money call options here. So what we are doing is we are writing the payoff on any arbitrary payoff that's smooth in this sense as a linear weighted average of these payoffs on puts and call options out of the money. There's this linear term and then a constant. Okay, you can actually think of this as a futures precision, and you can think of this as a weighted average of different options positions here in the put and here in the call. So having this payoff, G payoff on the futures contracts is equivalent to having lots of puts and options position weighted in this particular way, and a futures contract or futures position and some bond position that gives you a fixed amount. Okay, so this term drops out when you take the expectation and you stick F0 in here. There's not expected to be a drift in the futures price. This term disappears, and here this expectation you can take inside, and if you look at the expectation of this, G, that's exactly my price of the put option, and over here the call option. So if I use this M0 or K to indicate at this strike price, it's either the call or the put that's out of the money at that strike price. This is then the market price of that, and those I can go in and observe. Across all these different strikes, I can go in and observe the put and call price in the marketplace with a very good approximation. So these are observable. I pick my own G function. It just has to be a smooth function, so I know what the second derivative is. So I can kind of evaluate this expression directly, and here's just a constant. So this becomes a useful expression that expresses the price of this payoff in terms of the cross-section of option prices. It's a weighted average of the option prices plus this constant. Well, this G has nothing to do with volatility yet. I would like this G to have something to do with volatility. How can I do that? That's the second part. So this is one piece. I'm going to combine it with the second piece. And the second piece is using Ito's lemma on the dynamics of these futures price. So the futures price will have no drift term. So if you ignore jumps in this setting, there will be a representation where the futures price evolves as sigma t dw. Okay? The drift term has disappeared. because I'm looking at the futures. Use Ito's lemma on that. I presume you know Ito's lemma. And you will get that the expected value of this, not written in the integral form, becomes this term. You either know this or you don't, and I'm not going to be able to teach you in the few minutes I can dedicate to this. But Ito's lemma basically says that this will have to hold true, and I take expectation in on each side, and I get this. Now looking at this, here we have expected value of df's. Again, these expected changes in the futures price are going to be 0. So this term is going to cancel out. So we're only going to have this term over here, just by Ito's lemma that says something about the evolution over time. Okay? That's going to have the sigma in it. This second order Ito term has the sigma t squared in it. It's weighted by f squared times g double prime f. So there's this nasty thing in front, but at least I'm now getting an integral from 0 to t of sigma t squared. Okay? That's useful. If I can choose my g function appropriately, maybe I can knock that one out. I can get this to disappear, and I only have sigma t squared. And that's going to be the key. Okay? So I can do that, we hope. But for what I have for now is that since this term disappears, we just have to have this representation here. Now, this is the second expression for what the value of this payoff is. If you combine it with what I had here, down here, okay, this is one expression. This goes in the cross-section of the strikes. This is actually an intertemporal one that aggregates over time with the sigma squared appearing. I equate those two terms. This 2 multiplies on the other. This GF0, see, it's here and it's here. When I equate the 2, it just cancels out. So you are left with this expression, which has a time dimension, sigma squared, and you are left with something that's given by the cross-section of option prices across the strikes. So this is the fundamental equation that you play with. You just have to find the right g function. Momentarily, I'm going to do that. Okay? Momentarily, I'm going to do that, and I have enough time. That's great. Let me first introduce a concept that is closely related to the variance swap contract. So I'm going to call that the barrier variance contract, and I'm going to use it at the end of the talk now, so it's not superficial, but I'm extremely much going to be dependent on it in the next lecture. Okay? So imagine you have a contract that only introduce first this indicator function. It's 1 when the futures price is below a certain barrier, otherwise it's 0. So when it goes above the barrier, you don't pay anything, but as long as you're below the barrier, you have the usual contract. Okay, so that's called a barrier contract. And you can introduce something we call barrier integrated variance between 0 and t. You integrate as before sigma t squared over the whole interval, but you only accumulate when you're below the barrier. If you go above the barrier, you get 0. So it accumulates the variance along the path, exactly as we do with integrated variance, except when we go outside this region, we stop, put it to 0. Okay? Well, it's kind of weird, maybe, but if you let b go to infinity, so if you let b here go to infinity, there's no constraint on you. This will always be 1, and you're back to the regular variance contract, because you never get to 0. You're always below infinity on the futures price. Well, that means in the limit, we actually get exactly this quantity we might be interested in mostly, but I'm also interested in these barrier contracts and barrier variances. Okay? So it's just a generalization. Here is how it will work. Imagine this is the barrier we have. We integrate variance all along this path. You know, the sample path variation. We take squared returns, accumulate them all along this path until we get to here. Now we break the barrier, and this will be 0. So we only get the variance that's accumulated between here and here. Now I drew a second barrier. Once you have the concept of one barrier, I can have a barrier on the downside as well. Now I have a corridor. That's called a corridor. And here I will be accumulating variance up to here. Then it becomes 0. And then accumulate variance 0 here, and then accumulate variance and 0 here. So now you get corridor concepts as well, all of this, which is straightforwardly defined as well. Okay, I said I wanted to find this g function so I get integrated variance or barrier variance out of it, and that happens now. So we have this general equation. Now if I choose, what do I need to choose g to knock this guy out? I need to take a double derivative of something, and I need to get 1 over f squared, basically. Well, if I take the log of f, I differentiate it, I get 1 over f, and then I get minus 1 over f squared. So if I take minus log f, it's going to work. Okay, and that's what I do. I take minus log f. I divide by b because I wanted to also apply for this barrier, and I want it to be smooth when there's a kink in this barrier. But, you know, in the general context, you don't even need the b here. Okay, so this is the function I choose times the indicator function. These are linear in f, so if you differentiate twice, all of this just disappears, and you only get this 1 over f squared out of that. So apply this g function here and here. Take the double derivative with respect to k, double respect to f here of that g function, defined either on f or on k. And these two sides of the equation are easy to evaluate, and they become, well, one of them becomes this. Okay, that's the expectation on the Q measure of sigma squared times the indicator function. Now, if my barrier was infinity, so this would just always be 1, I have the integrated variance. More generally, I have exactly this variance counted as long as I stay below the barrier, and only below the barrier, but I get the cumulative variance in some segment of the underlying price domain. And over on the other side, I get this this is the market prices of the options divided by k squared. This comes from double differentiating this guy, okay? So this is a weighted average of the out of the money call and put options across all the strikes from 0 to infinity. Now, in reality, we're not going to have strikes very close to 0, and we're not going to have strikes if B was infinity, close to infinity, but the beautiful thing here is B just pops up here. Okay? So if you're interested in the barrier, you could actually stop when you think you have reliable options and not go beyond that. So you don't have to integrate to infinity, and you still have a well-defined concept of what it is you're measuring over here, namely the integrated variance up to that barrier. Okay? So you can actually kind of control the region you need to integrate over in order to say what integrated variance concept you are looking at. So repeat that. One of the problems you get when you want to estimate this thing here for the integrated variance altogether is you should integrate from 0 to infinity. At 0, we have very few option prices for strikes close to 0. We have very few option prices for strikes close to infinity. Now, that doesn't matter too much because the risk neutral density is also close to 0 there. But if there's a long tail, it's still this cumulative density could still add up to something that you are ignoring because you don't have option prices. And the Chicago Board of Options Exchange actually truncates when they have no more reliable prices out there. They stop accumulating variance out there and just gives you the VIX measure up to that. So in some sense, they're actually using a barrier or corridor variance when they calculate these measures. In any case, you can come up with this. If I wanted to define the barrier implied volatility, you need to take the square root of that. And that's, if you take that to infinity, the B to infinity, you have the model-free implied variance, which is basically the VIX when you take the square root. Okay, so that's how the options exchange would get the measure. They would create as best they can. They would replace this integral by a sum over the strikes that are available, linear interpolate between, and calculate this sum, and take this to multiply by 2 and take the square root, and that's it. That's how you infer out what the model-free implied variance or the VIX is on a given day. That's how you could get it more generally. If you only do it up to strikes that go up to B, you can get the barrier implied variance. Okay? So these are literally kind of market prices of, notice this is literally the market price of the barrier variance, or more generally the model-free implied variance over that horizon. Okay. Let me also introduce the corridor variance. I'm right on time. Let me just introduce the corridor variance, which is where we have the barriers B1 and B2, one below and one above. How will you price that? No surprise, we just need to integrate from B1 to B2. Again, let me reiterate, in reality, that is kind of what they do when they compute model-free implied variances. They go to a lower bound where they can find strikes that are liquid and reliable, the upper bound, and then they integrate within that and saying the risk neutral density is close to 0 outside of here, so we don't take it into account. But they actually do truncate. We find some problems with that because the way they truncate depends on whether the options are liquid or not, so you got to get a time-varying domain and some noise in this measure in terms of what you compare from one day to the next. If you have more options trading, you get a wider domain computed into this measure. When you're less, you get a lower number because you're including less options. Everything else the same. Okay, but you get this corridor pricing concept exactly the same way. Okay, now I would actually advocate that this corridor implied variance has is an appealing concept. You can control what variance you're measuring within certain bounds, because if you control the bounds instead of letting the market liquidity determine how far out or in you go, let's find an economically motivated criterion for when we stop measuring variances in each end. And one way to think about is to to more generally ponder how should we choose these barriers to get a good volatility measure out of it. And so for a given corridor, say we choose a given corridor B1, B2, and we only accumulate variance as long as the futures price going forward stays within those two ranges. When the volatility increases, imagine two situations. One day we have this, and then the next day volatility is much higher. What is going to happen is the return variation will be higher per unit of time you're within that corridor because the volatility is higher, so you're going to see more squared variation along the path. Second, you will run out of that corridor more quickly. There's a bigger chance that you will, because volatility is higher, that you will actually move beyond B1 or B2 on one side or the other. And so you're going to get a lower measure because of this. You're going to get a higher measure because of that. So that makes it hard to figure out how to calibrate that corridor if you want to have it a fixed dollar amount or percentage amount out on each side of at the money or something like that. So what you can do is you would want to think of it as you want to measure, if you want to use this corridor implied variance of volatility as a measure of the volatility level and make it comparable across days, you would have to adjust the width of this corridor in a sensible way. The way we think about doing it is, well, we have the whole risk-neutral distribution. Okay, we have the whole risk-neutral distribution. How do you compare days with different volatilities? Well, you kind of think about, I want a corridor where there's only 5% chance we go outside on the left, and we have 5% chance we go outside on the right. Then if I do that every day, I'm using the same barrier in a probabilistic sense in terms of how likely in the next month we are to stay within that range. And that's what we do. We find a particular fractile of the risk-neutral distribution, which we get day by day, and we look at these option prices that reflect volatility going forward 1 month. And we pick different fractiles. We can pick the 0.25 or 2.5% or 25%. One would just cover the 50% in the middle, right? How does the market price volatility that will take place within the 50 percentile right in the middle? Or how does the market price the volatility that will take place within the 2.5 out to 97.5 percentile? Okay, so you can kind of construct these measures. And here is what they would look like. Here we have a day with the volatility is up high, the implied volatility is up high, you have the skew. Here it's low. If you map that into the risk-neutral distribution, in order to get, I guess here you have a 5% level on each end. Here you need to put the barrier here, and there's 5% to going out here, 5% to go out here at maturity, outside of the barrier. When you have the more volatile distribution, volatility is expected to be much higher, you need to have a much wider barrier. You go all the way out here and all the way out here. You see the distribution is much flatter relative to this peaked one here. Okay? So in order to get a reasonable volatility measure in terms of what the model is pricing, you would want to compare the volatility that takes place in this range to the volatility that takes place in that range over the next month. Okay? So that's what we do. Okay, so now this was the big theoretical jump where we start looking at volatilities that take place in certain fragments of the underlying domain. Let me also say, once you do this, there's an additivity property. If you look at the realized variance in this range, and then you add the realized variance in this range and the realized variance in this range, you get back the full total model-free implied variance, right? So we literally splice up the expected variance in different parts of the domain over the next month into pieces, into corridors or slices or barriers. Okay, so you can kind of say volatility is expected to be more in that range and lower in that range going forward. So you can decompose the total variance that's going to take place according to these principles. And that additivity principle is very nice. You can do that both for the realized variances and you can do it for the model-free. Okay, so we find that very useful. And I will apply that repeatedly in the next lecture. Okay, I have 15 minutes to talk a little bit about option implied variance measures as forecasters of volatility, as in particular realized variance or realized volatility that's going to take place in the future. As Tim, I think, convincingly argued, of course I think so, is that we should use as a benchmark the realized volatility over the next month to see if these volatility measures are any good. Okay? So this is an age-old question, and people have written papers on this for about 20 years at least, since reliable option prices came out, in terms of how well do the option implied Black-Scholes measures forecast volatility versus gauge models and things like that. This whole thing is now shifted to how well do model-free implied variance or corridor variances forecast realized volatilities going forward. It's the same age-old question, but refined techniques in some sense. Okay, so as techniques and measurements improve, we rephrase the questions, but the same fundamentally underlying issue. Now, let me indicate the different types of implied variance measures I've talked about. So we have the VIX or the model free. The VIX is literally the one that the Chicago Board Option Exchange gives us. I have some qualms about how they calculate that. I already kind of talked a little bit about, I'm a little worried if they get extra noise in. They are allowing the range in which they calculate this measure to fluctuate a little randomly. I think there's some noise in the way they do it, but they fixed the way, and since market participants know this way, they can't really easily change it. So they kind of stuck with that, and it's probably, for their purposes, okay. But if you want to really think of it as a model-free implied variance with the optimal properties, I'm more comfortable applying my own extracting risk neutral density and pricing back up and computing this cross-section of this weighted average option prices our way. So what I'm trying to say is we have our own model-free implied variance. It's going to be highly correlated with the one you can see every day published by the CBOE, but it's not identical. So I have my own measure. What are the advantages of that? It's model-free. It's going to capture the full domain of volatility. This is kind of what we're interested in, the whole variance. However, in reality, you do need to truncate these measures. When you extract things from options, you don't have strikes all the way out, and theory assumes you do. So when you do this in practice, you are going to truncate or extrapolate. If you truncate, but you want to calculate the tails, you have to make some assumptions about what the risk neutral density looks out where you have no option prices whatsoever. And we're afraid that you might make mistakes when you do that, but we do it ourselves to come up with that, because we need to integrate from 0 to infinity. But down here, when we use the corridors, we actually truncate at a point where we still have reliable option prices, and we get a reliable risk neutral density for that part where we are calculating things. Okay, so and another thing that happens when you do these things is that you go out of the money on the put side, and the volatility premiums, you see this smirk all the time. Well, that means the option prices further out of the money on the put side especially are much more expensive than the ones at the money, which means instead of having the same volatility as at the money on in Black-Scholes, you're going to get a higher volatility, more expensive options theoretically. Not surprisingly, when you do the calculations, you end up with a measure that's a bit higher because you're averaging in across the whole smile. You're not taking the low point, which is at the money, but you were getting these higher values as well. That is why the measures aggregates up. So it's not obvious that these out of the money put options are really informative about future volatility. Maybe they have more to do with a risk premium that people are willing to pay for being insured on the downside. If that's the case, if you want to think of them as volatility forecasts, they could be problematic, and we might actually be better off with an at-the-money measure. Okay, and noisy, as I already mentioned. Black-Scholes, we've already talked about universal simple pricing standard, invalid model assumption, uses liquid at-the-money options. So you don't have these noisiness issues with the Black-Scholes. Corridor, you can make those model free. It avoids noise if the corridor only covers liquid options. So that's going to be my preferred way to go actually these days. And but it captures only part of the volatility domain. That's a caveat. We are not trying to say something about the range where we can't estimate things. The hope is that we can still get something that's very highly correlated with actual volatility and use some scaling of that. So let's see how it goes when we start comparing these as actual forecast for volatility, which is after all the focus on these lectures. So first of all, I mentioned there is actually a viable market for variance contracts. And so as an aside, this is very interesting. There are lots of commercial/academic presentations by the exchanges in Chicago that tries to pitch this idea that you should trade variance as a portfolio manager. And the short story of this is, if you are long the market, so you're a portfolio manager that do this for a pension fund or something like that, and you are long equities, well, it would be nice to have a built-in insurance contract. So when equities drop, you actually get a high payoff. Well, maybe it turns out these variance swaps realized volatility shoots up when the market drops. So you can see market has dropped in 2008 and volatility shot up. So if you add these variance swaps, you buy this realized variance, you get a huge payoff on drops in the market. So they actually argue you should put 5 or 10% of your value into these downside insurance, and you get a much better mean variance trade-off. You lower the volatility of your portfolio with almost no cost in terms of the expected return. So you get a much better Sharpe ratio out of this because you get insurance on the downside. And so if you have a long position, you should buy these variance swaps. On the other hand, it turns out that it's very profitable to sell variance swaps to people. So if you don't already have a long position, you might take the other side and sell these things to these other guys, right? You want to take a short position because it turns out people overpay for the options. So you should sell options or variance swaps to people, and they might then use it as insurance, right? So they want both people to both buy and sell, right? So they want to create a liquid market. They're sitting in between as market makers and make money on it. So and it's, it's working, and you can argue it's not completely silly, both of them. So anyway, they're really trying to pitch this. It's just a side story. Okay, let me get to this last piece, which is looking at volatility forecast that comes from implied variance of volatilities. The data source I'm going to use, now I had to stop in 06, this, unfortunately not 08, which I'll do this afternoon a little bit more. I have data from the CME, as I said, CBOE is just the VIX, and then we need the risk-free rate for a few adjustments here and there and the option pricing, but not important. There are some advantages of using the futures and options. Let me not ponder that. So every trading day, we get the following measures, volatility measures, implied from options. So I said there's more than one implied volatility. Well, we already talked about the VIX and the model free that we construct ourselves that is very closely related to the VIX. You can also have the Black-Scholes, but I also introduced 4 corridors here. One that's very broad, goes from 25 to 75 percentile of the risk-neutral distribution, and one that goes all the way down to 2.5, so that will cover from the 2.5 to the 97.5. So they all centered around at the money, and they are symmetric corridors. All the way out to here, we have pretty good options prices. So almost for all these measures, we have a reliable inference about what the risk-neutral density looks like, how the market is pricing things as a function of the futures price on that date. So we find these volatility measures very reliable. You start getting noise when you get to the model free or the VIX. On top of that, as reference point, we have to compute the realized variance, which is the thing we're going to forecast. We're going to use that as subsequent realizations. You can do that using daily squared returns or high frequency 5-minute returns is what we use. This is more reliable, obviously, according to what Tim said, and he's right. And you accumulate within the trading day each 5 minutes, and then overnight you square the overnight return, because options price variance or volatility throughout the month. It doesn't just price it for the trading period. So we accumulate 5-minute returns in the trading period, and then we take the close to open squared return as well. So there's one lower frequency return that we have to add in to get a complete coverage over the month. Okay, so that's the definition of these two. So these are realized variance measures. We, in some sense, use this as control. These guys should forecast that for the month going forward fairly well, we hope. Okay, so here's the S&P 500. Here's the VIX and realized volatility. So here, immediately, I can give you some insight. See the realized volatility is down here, the green line. Almost everywhere, you'll see the VIX above that. So the VIX is an inflated forecast on average of where the realized variance is. Quite wildly inflated, actually. There's a pretty big gap between the two. Now, in premium language, what we would say is, if you get the realized variance, that's what you get when you buy a variance swap contract, you get the green and you pay the blue. You can see this is a rip-off. You're always going to pay more than you receive, almost always. There's a few instances where it jumps above. Okay, and in 08, late last year, you got some big losses if you were selling variance. So that's where you get the compensation. When you got unexpected huge realized variance, you would actually have made money for some months where the losses were dramatic on the S&P. So maybe this premium is an insurance for such wild event, but the premium does look big, okay? Here comes a table that's just descriptive statistics, and I'm not going to talk much about the interplay between realized volatility or variance and the VIX measures, but this is the basic facts in an unconditional sense. And what is remarkable is that you can see on average the volatility was 15% over this sample of 17 years. 15%, okay? This is the actual underlying S&P 500 volatility. The model free and the VIX would say it should be 19%. 19 versus 15 is 4% relative to 15. It's a huge percentage overvaluation. Okay, this is a big gap. Even though it's only 4%, it's 4% relative to 15, right? So it's more than 25% above what it's, quote unquote, seems rational. The model free, of course, our measure is very similar to that. We think there's some noise in that inflates it a little bit artificially, but we get a measure that's very high. If you look at the Black-Scholes, it's 16.5. It's also above the realized. That's actually a well-known fact. The Black-Scholes implied their volatility is on average a little higher than the realized variance. Okay, so that's a volatility risk premium right there. But that's actually an order of magnitude smaller than it is for this guy. Again, you know, the implied volatility at the money is smaller than it is outside, and since you're averaging to get the model free with a weighted average, you're going to get a higher number. If you look at the corridors, you see that the wide corridor is big. The wide corridor here is bigger than the model in the realized, and as you have to go all the way down, even CIV2, which excludes, let's go back and see, CIV2 is 10% and 90%, it excludes 10% of the probability mass on one side and 10% on the other, and still we expect, the option prices tell us there's more variance within those 80% in the middle than in reality happens over the 100% domain. Okay, so that's how much extra pricing there is a variance in the options relative to the underlying. Okay, so another thing to notice here is that these are just the realized measures. So of course, these are not expectations. The realizations have higher kurtosis and skewness than any of the expectation measures. That just says realizations are more volatile than expectations. Expectations kind of smooth over different outcomes. That's exactly as you would expect. And you also see these really high order correlations out to lag. This is 63. So if you compute this every day, you see there's a huge order correlation in all the implied volatility measures, but also in our realized variance measures. And this is really, really high ones, of course, because these are overlapping. These are monthly measures created with daily returns, so with the high frequency returns. So they are kind of built in. But even when you go beyond a month where this overlap is an issue, you get these very high order correlation features. That feeds back to Tim's comment. There's kind of long memory type features in the volatility dynamics. I'm not going to use that for anything. I just wanted to point out it's very much in the option prices. It's very much in the realized measures as well. So you can't forecast variance really well without putting that feature in there or doing something else that mimics a long memory feature. You can have regime shift or something else as well. Okay, so here are just some pictures. If you take these corridor variances and divide by the model free, the total one, these will always be smaller than, but what you see here is that this is the 50% in the middle, okay, CIV1. And it fluctuates dramatically. You can see some big shifts here in the implied volatilities that are pretty dramatic. What does that mean when it drops? It means that the variance we expect in the middle becomes smaller relative to the variance we expect in the tails. And so the tail volatility suddenly got a big jump. So people got concerned, started pricing volatility in the tails much more than in the middle. So something happened in the market that put a lot of volatility pricing out in the tails. Well, this is around the Asian crisis, so that's probably what happened there, right? That's probably the biggest move. If you divide by the Black-Scholes implied volatility instead, you get some more very nice pictures. You'll see here my corridor number 2, which is a 10 to 90%, I think, is very much the same as a Black-Scholes implied volatility forecast. So what this says is, in practice, the Black-Scholes implied volatility forecast is very similar to a corridor that only measures from 10 to 90% in my other concept. The corridor implied volatility concept is theoretically sound in the sense I know what I'm measuring. It allows for general arbitrage-free dynamics and stochastic volatility and jumps for that matter. Black-Scholes does not. But empirically, it is very similar, right? This is almost a flat line, and it's almost at 1 as well. So the Black-Scholes maps into something that empirically is very close to one of these corridor concepts that I've introduced. Okay, now I'm going to round up in a minute or two. Is it okay if we take another couple of minutes, Nicholas? Okay. So what do I get out of all of this? Well, there's a very large negative volatility risk premium. That is, when you buy a variance swap contract, you're going to lose money, or you pay more for it than it actually turns out to be on average. That's what we call a negative volatility risk premium. These different measures are highly correlated. As we move from C4 to C1, we move from the broader corridors to the lower corridors, we actually get more stable measures. If you want stable volatility measures, you've got to look at the narrower corridors that isn't as sensitive to twists in the implied volatility shape. At the money, Black-Scholes is essentially the same as one of my corridors. Rest of it is more or less what we've seen. All measures are biased for the realized variance. That means, and people do this when they do forecasts, they downscale the model-free or the Black-Scholes forecast to come up with a forecast for actual volatility because they know it exaggerates on average a little bit. So just take the average exaggeration or bias and bias adjust, and you can do that obviously. And so that's what people do. They run regressions like this, and we did so too. In-sample regression, predictive regressions, where you take the forecast and you see how well it explains. So this is really Minczasanovic type regressions that Tim already talked about. The forecast, and here the actual realizations. This is the forecast at time t, and this is the t+1 month actual realizations. We can have 9 different volatility measures when we do this. And since I'm going to be short of time, let me just summarize the evidence, and you can look at the notes, or you can go back to my paper with Bondarenko where this actually stems from, which is in the risk book. We can do this in terms of just the univariate regression, so we can compare two and see which coefficient dominates, which one has more explanatory power. We can look at the R-square of these things. We can also do auto sample, where we estimate these coefficients in sample, lock these coefficients down, and see how well it predicts auto sample without snooping. That's actually better to do that. And you can look at the root mean squared error in terms of the forecasts. You can switch in and out of samples to see if that means anything. And you can forecast volatility or log volatility or variance. Fortunately, you get basically the same conclusion depending on, it doesn't matter how you think of this variance you want to forecast. This is economically maybe the most sensible, but this is what Black-Scholes guys kind of do. And log volatility is statistically the most nice feature. So all 3 regressions have something going for them. Instead of summarizing the evidence here, let me just look at the R-squares. And what you will find is that in sample, the CIV1 and Black-Scholes and CIV2 tend to get the highest R-squares. Okay? So these are very good forecasts in some sense. The forecasts that are included up here, realized variance at the daily and high frequency level, are lagged, 1 period lagged. And people sometimes use that in the literature. They take, okay, we can create a realized variance forecast. It's not the ones that Tim and I advocate, where we actually have a model that says how you take lagged realized variances and forecast using a fraction integrated type model or something like that, or a HA model that Tim advocated earlier. But instead says the last month is what we predict for the next month, because volatility is persistent. Why not just take the last month and forecast the next month? Well, we know sometimes volatility is spiking, goes up, and we know there's mean reversion. So it's going to be a terrible forecast, and that's what you see up here. It's, if you just do these lagged realized variance measures, they're not going to do as well as the implied volatility measures. But that's a fake comparison, and I could talk more about that, I won't. Instead of going over these labels, let me just summarize it and end up. You can go back and look at this table here and actually see that the conclusions I extract from it are basically, at least given the evidence we have unearthed, about right. So the lagged 1 month RV, historical, people call that historical volatility, are the worst forecasts. Again, I can create much better ones that are at least competitive, if not better than the implied volatility measures using realized volatility techniques. If you want to do this, you should use the high frequency based measure, not the daily measure. You can look at the table and see that the daily measure is a disaster. You really want to get the benefit of high frequency data also when you use it as a benchmark for what volatility actually was. VIX turns out to be about the worst forecast you can come up with from implied volatility. It's also model free implied and measures the whole thing. It's also kind of bad. The very broad corridors are bad. The best ones are the narrow corridors, the ones that look kind of close, or Black-Scholes that goes to the extreme and just looks at the money. Turns out, if you want to think of them as forecasts, turned out to be the better forecast. This is robust over subsamples, no matter how you sort volatility. That is the high volatility regimes, the low volatility regimes, and the definition of volatility, variance, log variance, volatility, square roots. When you do encompassing, that means if I'm looking at the CIV1 measure or the VIX measure, do I get something extra by adding in what the historical variance was? And it turns out that I do. So this thing here adds value to the CIV1, but the VIX does not add value, right? So I have this best measure that is this narrow corridor, CIV1. This is if I look at these things, that's the implied volatility measure I think I can bias correct and get the best forecast out of. Now you might say, if I combine that with one of the other ones, I'm using more information, I should do better. Well, it turns out, even though VIX is a much better forecast than historical high-frequency-based realized volatility, if I add VIX into this, they're so highly correlated, I just get the same measure, more noisy measure of the same thing. So I don't need the VIX if I have my narrow corridor. Hence, it's important to understand these corridors can be good. But if I add in historical volatility, what the realized volatility has been, that actually has additional information. And you can look at that in the graph, and I do that in compassing. So that is interesting. There's something orthogonal in the realized variance measures relative to the options measures that says you should probably combine them in some optimal fashion. And that's where I would take the research going forward. Okay? So here, two final comments. Better use of lagged daily RVs using Arthemas or HAR estimations or other techniques would be competitive with the implied volatility measures. And what you really would want to do is you would want to combine these things. You want to use the best forecast you can do just from realized volatility and the best forecast you can come up with from options and combine them two in a sensible way to get an even better forecast. That is really something I'm looking at in my research, and I think that is a big research agenda. I should say this, what all I said comes out to seem very, very critical of this idea of VIX or model-free implied variance forecasts. Well, we need to keep in mind the VIX is not just put out there as a forecast of future volatility. That's not really what they're interested in. They're interested in what people want to pay for it. They're interested in about what people are scared of. They are actually interested in how people price these things. And it turns out there is a volatility risk premium that varies, and when volatility goes up, this measure inflates particularly much and becomes a poor volatility forecast, but it tells you how people are pricing credit spreads and lots of other risky assets around the economy. So there is a completely different volatility risk price gauge function of these model-free implied variance measures that is not in the Black-Scholes. And so there's a different economic function of that, and that's really what comes into play in the next lecture that Tim and I are going to share, where we are going to look at the model-free ones as an indicator of the fair price of variance or volatility according to the derivatives markets, which has a risk premium embedded in it, versus the realized variances that actually occur, which do not have that risk premium in it. So studying that difference gives you a way to look at these risk premium dynamics. Whereas if you want to look at just as forecasts, you're probably better off just using the Black-Scholes or using a very narrow corridor, maybe combined with realized variance. So this is the last slide. Black-Scholes can be used as a price quote device. They give sensible volatility forecasts with minor bias correction. They are all biased, the ones you can come up with, but they beat simple lagged historical volatility. Narrow corridors are slightly better than Black-Scholes. These are the ones I prefer. Corridor IV limits noise. That's because they are less noisy relative to these other guys, I think, and also gets rid of some of the very risk premium that in other contexts are very interesting. VIX is about the worst forecast, so when you see the VIX and it's forecasting volatility at some level, well, I'll take it with a grain of salt. It's actually not a terribly good one. You should exploit the information in these corridor barrier implied variances, I think, in different ways, and you should really combine it with time series forecast in the style that Tim talked about this morning. Okay, that's it.
I'm just curious, I agree completely that the VIX so as a forecast and the realized that there's all sorts of problems that we're going to highlight in the next lecture. I'm just curious if you could go back to the table where you sort of make that statement on. I didn't quite understand why that is. Can you try to go back to the table? Just look at the numbers.
You mean the table that I skipped over?
Yeah, I was just sort of
sure.
I just wasn't sure whether.
So here's the VIX. So in order to look at the coefficients, you just basically had to multiply its forecast by 0.75 to bias correct.
So it's in terms of the beta coefficient, that's what you mean. It's not the
No. The R square is kind of, they're also highly correlated, but it's completely consistent when you look through. So this 60, this 1% worse performance is, people underestimate what a difference in R square actually can mean for these things, because it's easy to get a high R square, because when volatility is high, these guys are all high, and the realized variance has these huge variations. So it's really deceptive to so if you, VIX actually does well. So see, we did this gives me a chance to talk about this. When volatility is low, so we split into when volatility was in the third lowest range in terms of the Black-Scholes implied, the medium and the high. The VIX is actually a good forecast. These are pricing errors, root mean squared pricing errors. So you want these to be low, okay? So it actually does really well when volatility is low. That is, seems like the premium is not inflating things very much, and it's actually the best one. I don't know how reliable that is. But when you go to the high, this is like 38 versus 35 and 34. So it really deteriorates when volatility is very high. It seems like this premium effect scales it up dramatically. So there's an excess premium when volatility is high, and people will get price volatility risk much higher. So that's really, so a refinement of this research agenda would say when volatility is high, we need to scale VIX down more than when volatility is low. That leads to modeling the volatility risk premium, so that we have to do what we're doing this afternoon. This was just a reaction to saying the VIX is a good measure by itself. Well, it's hugely biased when volatility is high. It's not that good when volatility is medium, but it actually is quite good when volatility is low. And that also means usually you're spanning the range that volatility is likely to go in very well within the barriers that they set up. So I think it's intuitive, but I didn't have the time to refine this since I was running out of time.
Last question, if you update this analysis of the recent period where you now have realized volatility to be coming in, I guess the results on the table dramatically change.
Dramatically is an overstatement. The R-squares drop. The R-squares drop. The model free will probably do even worse because it's just wild, because it's, well, it comes afterwards. So first it misses the big spike, and then it jumps up tremendously and actually overstates what the volatility is going forward. Even though the volatility has been incredible, 90% or 80% is almost unfathomably high. If you try it intuitively, 90% is the annualized volatility. You know, imagine it stayed there for a year. One standard deviation is 90%. So S&P can go negative if you extrapolate it very far. Well, if it's continuously compound return, it couldn't. But basically it says there's a high probability that the S&P 500 is going to be worthless a year out. Well, that's clearly not what the market thinks, but it thinks it's going to be so high over the next month, and then it'll come back down. But that was, even though volatility was extremely high, it exaggerated things. But I actually will have tables that speak a little bit to it, that's updated to 08 for the S&P this afternoon. So you will see a little bit of what you wanted, but not in the forecasting dimension, but the premiums. So the returns on swaps, variance swaps, so the volatility risk premium I'll be talking about.
How have you combined these methods in the lower part of the table?
Say that again?
How have you combined the methods in the lower part of the table?
How did I combine?
You have there VIX plus CRV1.
Right. So there's two volatility forecasts, right? Is that what you're asking? How that?
Yes.
It's just basically according to the regression before. So we run the regression, but you have two different predictors, okay? And if one is much, much better than the other, one is encompassed. So all the information in this one is in this one as well, and this one is more precise. You would expect this coefficient to be close to 1 and this close to 0. And you know, if you look at the daily and high frequency volatility, you get a coefficient that's 0 on the daily, and the high frequency get a 0.82. That basically says there's mean reversion because there's a positive constant here. There's mean reversion in realized volatility, and only the high frequency measure is able to forecast it. It has all the information that is in the daily measure. So that's the interpretation of that. So if you go down to this one here, when you add it into the VIX, you can kind of get the weight that's put on the two forecasts, and this is the daily lag volatility actually has a little bit to say as well here. So that's how I interpret it. Okay, and then outer sample, we lock these coefficients in, and then we look outer sample to see if you put this weight on one forecast and that weight on the other forecast and use that to forecast, how do we do in terms of root mean squared errors. There's lots of different ways you can do this, but this is an intuitive, simple way for a first cut at that.
I did not understand what is low, medium, and high. Is it a root mean squared error, or it is?
No, it's the volatility itself. So when you create the risk neutral density and the variance forecast over the next month, okay, I look at what is the Black-Scholes at the money implied volatility. And so over these 2,000 days, I say there's a third lowest of those, there's a middle section of those, and then there's a high volatility rates. And Black-Scholes is a pretty good indicator of where the market, in terms of being monotonic in the underlying volatility, it's pretty accurate in terms of classifying this as a high volatility regime relative to a low volatility regime. So I'm just using the Black-Scholes implied volatility to tell me over the sample when was volatility expected to be high or low or medium, and then looking at whether the forecast performance is different for high and low volatility regimes. And certainly for the VIX or the model free, it's much more accurate when volatility is predicted to be low. And I think there's some intuition behind that, but that's what the classification is. Again, I apologize because I had to hurry at the end and I didn't really explain the table very well.
Okay, I suggest that we shift all further questions to the coffee break, and we should thank the speaker once again.